We can start.
Good evening, everyone. Welcome back to our quantum algorithms using Qniverse webinar series. Before we dive into today's topic, the last week we had with us Ms. Jivita, who had helped us understanding quantum error correction. So before we move on to today's topic, few important questions, announcements regarding quiz questions for refreshing your uh, knowledge of what you have learned. Last 3 weeks, I understand that there were not posted. These quiz questions were not posted. I apologize for that, and hopefully by Monday we will post those week's quiz questions. And we are nearing the end of the series with only 2 sessions remaining. I encourage all participants to review the material from the last 12 weeks and the next 2 weeks. So regarding the participation certificates, once we complete all the 14 weeks, everyone who have attended our weekly sessions will receive a participation certificate. For that, we will circulate the form during our session, which you can fill it up for your exact name, what it has to come on the participation certificate. Regarding the Qniverse developer certification exam, the details are being worked out. So regarding the registration, how to register for the developer certification exam, and how to pay the fees, what are the exam formats and other information like dates, when it will be open for the registration, when will be the exams conducted. For all those details, please follow us our official communication channels like WhatsApp public channel, or you will be notified through our emails. And let's move on to today's session. Today's session is on introduction to quantum machine learning. Today we are excited to have Mr. Sachin Namdeo, who will introduce us to quantum machine learning. Mr. Sachin is a researcher specializing in hybrid classical quantum machine learning. He currently works as a project engineer in the quantum technologies group at C-DAC. His strong background includes an MTech in computer science and engineering with a specialization in artificial intelligence from DIIT Pune, where his thesis focused on quantum long short-term memory, uh, quantum LSTM networks. At C-DAC, he is actively involved in research on quantum convolution neural networks, pushing the boundaries of integrating quantum computing with modern AI architectures. His work is instrumental in advancing quantum enhanced learning models and developing algorithms at the intersection of quantum computing and artificial intelligence. As always, please keep the chat clean and direct your questions and doubts to Mr. Sachin via the chat feature. Over to you, Sachin.
Thank you for the introduction, sir. So let me share my screen. I think you are able to see my screen.
Yes.
Okay. So let's start. Welcome everybody to today's session on Introduction to Quantum Machine Learning. So this is the agenda for our today's session. We'll look at a little bit about classical machine learning. We'll see what are the pain points in that classical machine learning. Then we'll shift to quantum machine learning. Why do we need quantum machine learning? And then we'll see how can we encode our data from classical to quantum, which is very essential for quantum machine learning. Then parameterized or variational quantum circuits, which are used in quantum machine learning. End-to-end workflow, like how the QML workflow happens. Then the limitation and open challenges in QML. So what is machine learning? Now, machine learning is a field that focuses on development of algorithms and statistical models that enable computers to perform tasks without explicit instruction. Now, how do they do that? They analyze and learn from large data sets, and then These models would identify patterns, and upon those patterns, it would make decisions and then improve over time. As you already know, machine learning is widely used in various fields, including finance, healthcare, and technology, also to automate some processes. Now, how do we define machine learning mathematically? Now, machine learning can be defined mathematically as a process of optimizing a model F that maps input data to output labels by minimizing a loss function. Basically, what you have to minimize is this loss function. This f of x here is what your model is going to predict. This y here is the actual or ground truth. And this is the expectation value of, basically we have to minimize this expectation value. Now, what are the types of machine learning? First is supervised machine learning, where the model is trained on datasets where you know both the inputs and their corresponding output labels. So, for example, there is regression and classification. Now, there is one more type called unsupervised learning, where model is trained on dataset where only the input data is available. You do not know what the corresponding targets are. So, this falls into clustering. K means clustering. Then there is something known as reinforcement learning, where the model learns by interacting with an environment, and then it would receive rewards or penalties based on the action it takes. For example, chess, if you have a game of chess, that environment would be the chessboard, and upon the model would take give move, and depending on whether it is a best move or the worst move, it would get rewards or penalties. Now, supervised learning, there are two types: regression, that is, you predict a continuous numerical outcome, usually linear regression, polynomial regression. Classification, where you predict discrete categories or labels like cat or dog, 0 or 1. Yeah, examples include logistic regression, support vector machines, decision trees, etc., k nearest neighbor, etc. So what happens is you take an input, you have an algorithm, whether it be regression or classification, and you get a logic. And using that logic, you give new inputs to it, which would give you the output or these predictions. Then there is unsupervised learning, where you group similar data points based on features. It can be based on distances, but there has to be some similarity between those points. Like if you see here, these red circles are much more similar, so they are grouped into one class, and these yellow squares are grouped into one. Now, there is also something called as dimensionality reduction. Now, let's say if you have 1,000 features and you want to reduce it to 32 or 64. So you use something called dimensionality reduction, which the example is principal component analysis, where you are able to reduce from 1,000 features to some 32 or 64 features, whatever you want. Use cases include customer segmentation and anomaly detection. Then reinforcement learning, where your agent learns optimal actions through interactions with the environment and thus maximizing the rewards. So let's take the example of chess, as I had said. So this environment would be a chessboard. The agent would make a move, and depending on the if it is a good move or a very bad move, it would get a reward. And this would go on until it has maximized the reward. So use cases are game playing like chess, robotics navigation, etc. Now, what are the bottlenecks of classical machine learning? What are the pain points? If you see, classical in our classical data, the volume of the data generated is very high, and the speed at which the classical data is coming to us is also very high. So, thus, training on massive, continuously growing data sets would often exceed memory or processing capacity. We can use batch-based learning, but that would require repeated passes. Another thing is feature engineering overhead. You have, as I said in PCA, principal component analysis, you have to shrink your 1,000 features to 64 or 32. Thus, that is also a manual selection. You have to manually select, extract, and transform those features, which is a very time consuming and error prone thing. Then there is curse of dimensionality. As the number of features increase, so thus the dimension increases. Thus, distance metrics become less meaningful. Like if you do for k-means and everything, they would become less meaningful. And thus, model performance would degrade. High dimension spaces exponentially increase the computational cost as well. Then there is something called as training time and conversion. The bigger your model, the more dataset you have, the more training time it would take. As well as if you, let's say, if you have a non-convex optimization where you have multiple local minimas but one global minima. So any deep neural network can get stuck in local minima and would require many epochs or you have to run it again. Scalability and parallelism limits. Many classical algorithms will not be able to parallelize efficiently across thousands of cores. And then resource constraint. To run all these bigger models with all those big data sets, you require GPUs or high performance clusters, which are very expensive, and thus training the state of the art models can consume significant power. Thus, it would require much more energy. Now we come to the introduction to quantum machine learning. Now, what is quantum machine learning? Basic definition is, in quantum machine learning, you and develop quantum algorithms to solve typical problems of machine learning using the efficiency of quantum computing. Current most common term would, if you go and search, current most common term would be quantum enhanced machine learning. Like whatever classical algorithm I have, I'll enhance it or tweak it with quantum computing. Now, how QML is achieved? You design parameterized quantum circuits or variational quantum circuits. We look at its definition, and these two are a little bit different. And then executing the set circuits on quantum simulators or actual quantum hardware. Now, why do we need QML? There is going like some quantum algorithms, like some classical algorithms, sorry, like SVMs. The kernels of SVM require O(n) square to O(n) cube. Thus, it is very much time consuming. So, some quantum algorithms, such as if you shift to quantum SVM, would offer exponential speed up over their classical counterparts. Quantum parallelism is also there, like using superposition, which is very useful for high dimensional data. We can have very high dimensional data and we would require very less number of qubits if we use amplitude encoding, which we'll talk about. Then sampling advantages. Like quantum computers can efficiently sample very complex distributions, thus would enable quantum generative models like Boltzmann machines to potentially outperform classical counterparts. Basically, the quantum generative models would create a complex distribution where you would just need to give classical data and it would automatically convert it to quantum data. But this is very future. This is in future, so currently it is not possible. Then overcoming classical limits, like as we decrease the size of the transistors from 1 nanometer to more less, so we would have quantum tunneling effects. Thus we would have classical computers near their limits in power and miniaturization. So now one thing in initialization of qubits, like especially for quantum machine learning, you have to initialize the qubits to state 0. It is a standard practice in quantum computing as well, but for quantum machine learning this is very essential at it, as it provides a deterministic start. The state 0 is well defined. Like if you do not have all the qubits initialized to 0, it would not provide a consistent starting point. Thus, if you have a consistent or deterministic starting point, you would have a deterministic end. Clarity in mapping, as it ensures that encoding process is very straightforward because everything is in 0 and there are no pre-existing entanglements or superpositions that could complicate the transformation. Error minimization, as we are starting in 0 state or a deterministic state, which would reduce the potential for initialization errors. Thus, which would reduce the errors that can propagate through the circuit if initial state was complex. As well as classical bit analogy, because in classical computing we also initialize everything to zero. Thus, initializing everything in a quantum computer to get zero would provide a straightforward analogy. Now the challenge comes: how do you translate classical data to quantum data? Our, our world runs on classical data, which is numbers, tables, images, text, etc. But quantum computers work in completely different language, that is amplitude, entanglement, and superposition. So thus, we must encode this data into qubits before any quantum magic can happen. So now why encoding matters? As I had said, quantum hardwares only understand amplitudes, entanglements, and superposition. Thus, we need to properly encode our classical data into quantum data. So without proper encoding, you won't be able to leverage the quantum speedups. Thus, if you do not have a proper encoding, you would have deeper circuits to properly encode it. And the more deeper the circuit, the more error prone it is, and more wastage of qubits would happen. And if you use a good encoding, you would have a compact or very small circuits. You would have a very higher accuracy, and you would get results much faster. So let's see what are the methods to encode our data from classical to quantum. First method is amplitude encoding. You can think of it as a compression master. So what happens in this is it packs an entire data vector into amplitudes of multi-qubit state. Like let's say you have 1,000 features, and if I use amplitude encoding, I can encode my 1,000 features in approximately 10 qubits, which is very much useful for today's applications. You can think of it as zipping 1 GB file into 1 MB archive. So how you do amplitude encoding? You normalize your data vector, so its squared entry sum to 1, that is its probability sum to 1, and then prepare superposition where x of I is your data, and I here is how many is the state. Like let's say if I am doing amplitude encoding for two states, so I would be 0 0 0 1 1 0 and 1 1. So what is the pros? It is logarithmic qubit scaling. For 1,000 features you only require approximately 10 qubits, but it requires a complex state preparation, and it requires precise normalization. So now there is another method called angle encoding. It basically represents each data value as a rotational angle on a qubit. Basically think of at what is the, like let's say our hand is at 3 o'clock, so the encoding would be 3. Now how do you do angle encoding? You have to normalize everything, and then for each feature A, you apply a rotation gate on it by giving a theta of A, what is your value, multiplied by scale. That is how you have normalized. Like you have to normalize your data and then give it to the rotation gates theta, and thus it would be encoded using angle encoding. You can also use multiple rotations like X rotation, Y rotation, or Z rotation, or a combination of these RX, RY for richer mapping. Now the pros is it is very simple. The circuit is very simple, and if you are a newcomer into quantum machine learning, it would be very easy for you to do it. But it is linearly qubit scaling. So as your number of features increase, like from 5 to 6, so your qubits also increase from 5 to 6. And then there is one more method called basis encoding, where you directly map each classical bit into a quantum state. Like let's say if my data is represented like this, what I would do is this: I would apply an X gate and get it into state 1. This I would leave it as qubit, for that qubit as 0, then apply again X, apply X gate here and leave it as it is. Thus this whole state would be encoded as get of 10110. Now pros it is very trivial to implement. As you can see, you just have to apply an X gate or leave it if it is 0. And minimal circuit depth is there because only one layer of X gate would be there. No compression is there, and it would need as many qubits as bits. So if your data, if you convert your classical data into binary, and if it has a very like a lot of bits, so you would need that many number of qubits as well, and thus it is very impractical for large data sets. So this is a little bit comparison about all the three types of encoding. Amplitude encoding requires log of 2n, log with base 2 n number of qubits. The circuit complexity is high, compression is exponential, and you can use this for high dimensional data, especially like quantum principal component analysis, where you have to compress your number of features. Then there is angle encoding, where you require n, so n number of features, n number of qubits. So you can use this for very small scale of feature sets like 10, 20, not more, and thus it is useful for variational quantum classifiers. Then you have basis encoding, where it also requires n qubits, where it has minimal circuit complexity, but it is only for binary data and is especially helpful in Grover's search. Now, how do you choose which encoding to use? So let's take the data size and dimensionality as one of the metrics. So let's say if your n, that is the number of features or your dimension of your data, is very high than your qubit budget, so you can use amplitude encoding in that case. But if your number of features or your dimension is small and you value simplicity and it is approximately equal to your qubit budget, then you can use angle or basis encoding. There comes hardware constraint as well. Like deeper circuits would be more error prone on noisy devices. Thus, you cannot use amplitude encoding on actual NISQ era hardwares, but you can use angle encoding because they have shallow circuits. And developmental effort, because amplitude encoding requires more engineering time as compared to angle or basis encoding, which is very quick to prototype. Now, you have heard about encoding. Now, think of encoding as just loading your data from classical to quantum. You haven't performed any, you haven't revealed any hidden details, you haven't performed feature mapping, like how one feature affects the other. So what do you use in that? You use something called as quantum feature maps. You can think of it as placing a you can think of encoding, basic encoding principles, as placing a camera in front of your data. But feature maps would focus and reveal hidden details. So a formal definition of a feature map is a parameterized quantum circuit that embeds classical data into quantum state. Its key purpose is basically to project data into higher dimensional quantum space and amplify certain nonlinear patterns. You can also use these feature maps as kernels for quantum algorithms like QSVM. So how does a feature map look like? So basically parameter assignment is there. You basically your data, after normalizing it, you treat it as a theta, and then you that would be given to as gate angles or phases. Then you have single qubit layers, rotation gates in R, Y, Z, X, or even a combination of them to encode your data. Then entangling layers would be there. You can use control node, C node gate, CZ gate between the qubits, and then you repeat this. Basically, what you do is you create a Hamiltonian or the physics of your data to minimize, and upon that you create your quantum circuit, and you can repeat this layers multiple times to enrich the embedding, and then you measure sample in computational basis, which is basically Z basis, to obtain feature vector. Now some of the feature maps that you can use, one of it is poly feature map. Basically it applies simple rotations around XYZ direction on each qubit using your data. So you can rotate qubit by data driven angle as the theta about X using rotation X. You can also use Y and Z gates, uh, RX and RZ gates, and then you can optionally entangle them with CZ gate, controlled Z gates. So basically it helps to 3D sculpting of your data. You are able to capture each feature from three directions, and thus it also reveals any hidden patterns which are there. So if you see, this is one of the example of polyfeature map. This is Z and YY polyfeature map. If you see here, this is one layer. Sorry, yeah, till here is one layer, and this is the second layer. This is a two-layer polyfeature map of Z and YY. So now ZZ feature map. As you have seen that we had used Z and YY. Now let's say if you use Z and ZZ poly. So basically it gives you a ZZ feature map. Now what it does, it links pairs of qubits so their states shift together based on their data. Similarly has was there in the poly feature map. Now, but instead you use Z and Z basis. Sorry, in Z direction. Then rotate each qubit by its data driven angle about Z axis. Then you apply controlled phase gate ZZ between the qubit pairs and repeat if more links are needed. Basically, it helps to create a social network of features, and thus if one feature changes, let's say feature 1 and feature 3 are connected, so if feature 1 changes, then the feature 3 would also change depending on the change in feature 1, and thus it also directly encodes your relationships A to B in your data. As I had said, if feature 1 and feature 3 are related, it would directly encode that. Now this is one of the example of ZZ feature map for depth 2 or two layers of ZZ feature map. If you see here, this is one layer and this is the other layer. Now basic encoding, what amplitude, angle and basis encoding versus your quantum feature maps. The purpose of basic encoding is to load your data directly onto your qubits, but it does not transform it. So instead, a quantum feature map would transform and enrich your data so that hidden patterns would become much more clear. Circuit is very much simple. You can use one rotation or data loading per gate, but this has layers of rotation gates plus gates that tie qubits together, that is entangling gates. Feature space, it basically keeps the same dimension but it as your data, but in here you can project it to a much larger dimension. Basic encodings would only capture linear features effects, but this quantum feature maps would capture complex and multi-feature relationships via entanglement. And when to use, basically if you want to use quickly demo it, or basic state preparation is there, but for machine learning tasks, especially quantum machine learning task, you need quantum feature maps. So now we come to trainable or parameterized quantum circuits, which are the basic building blocks of your quantum machine learning applications. Now think of these parameters like a tuning knob on an instrument. You have to tune them in such a way so that your input is harmonized with your output, output with the desired labels. Thus, it would give you correct answers. So how basically a parameterized circuit is done, like it is trained. You initialize, you start with a random parameter setting. As is the case for classical machine learning, you have a random weights, random initialization of weights and biases. Thus, in similar to in quantum machine learning, you also start with the random parameter settings. You evaluate, you run the circuit, measure the outputs, and compute a cost function. As is the case for classical machine learning, you start with a random parameter, you run the model, you measure, and then you compute your cost function. Then you update, can use classical optimizers, example gradient descent, to tweak the parameters. As is the case for classical machine learning, where after you have got the errors or the cost, you do use classical optimizers to get the gradients, and then you update the parameters, and then you iterate over it. You do this process again and again until the cost or your loss converges to a minimum. Now why it works, you can think of it, it is analogous to classical neural networks weight tuning. And also quantum operations would offer richer transformations, thus potentially capturing complex patterns. Now the building blocks of quantum ML. Now you have encoding, variational blocks, and measurement. So basically in your quantum circuit you would have data encoding part, where either you can use amplitude encoding or angle encoding. Then you would have processing layers or the actual variation blocks, which would house your actual parameters which you have to train. The parameterized gates are nothing but your rotation gates Rx, Ry, Rz, whose angles are trainable. These theta, phi, and psi are trainable. That is, they changes according to the iteration. Then entangling gates, you can use C0, CZ gate to create correlation between the qubits, and then you can layer them as well to increase the expressivity. Then you measure one or more qubits in computational basis, which is basically Z basis, and then you aggregate these measurements. You can take the average of it into predictions, so that you are correct. You can correctly predict the class label probabilities, and then you can use classical post processing as well. So now we come to parameterized quantum circuits. So parameterized quantum circuits are circuits where gates are defined through tunable parameters like theta, and thus are a fundamental building block of near-term quantum machine learning algorithms. That is the current era. They are interchangeably called variational circuits or variational quantum circuits, but there is a difference we will see. And as all quantum gates used in a quantum circuit are unitary, a parameterized circuit itself can be described as a unitary operation on n qubits. Basically, why we use parameterized quantum circuits is basically to encode our data, like the feature maps, where parameters are determined by the data being encoded, or as a quantum model, like variational circuits, where the parameters are determined by the optimization process. Now, PQC versus VQC. You may have heard these terms a lot. So PQC is nothing but parameterized quantum circuit, and VQC is variational quantum circuits. So basic definition is PQC is a broad concept which encompasses any quantum circuit with adjustable parameters. But VQC is a subset of PQC, which are specifically designed to be optimized using variation, hybrid, like that is quantum classical approach, or basically classical optimization. Variational quantum circuits would always involve an optimization process, and parameterized quantum circuits may or may not use a optimization. Basically, the term variation refers to the use of classical optimization. Now, this is a typical VQC that you can use. If you can see here, these theta, phi, mu, these are the parameters that you need to update or tune. Thus, this can be a typical PQC that you can use for quantum machine learning purpose. Now, let's say a person X has designed a quantum circuit, and a person Y has also designed a quantum circuit. Now, how do you differentiate between them? So there are two metrics you can use to differentiate. First is expressibility. Now, what is expressibility? It basically measures the ability of a variational circuit to approximate any quantum state in the Hilbert space. We'll see with an example how. Then, if you have a high expressibility, the circuit can explore a large portion of state space. Thus, your circuit will be able to generalize your data much more as compared to a low expressible circuit. Thus, if you have low expressibility, it would be under parameterized and would not be able to represent target states correctly. That is underfitting. If it is too high, it may suffer from barren plateaus and overfitting because of noise. Barren plateau basically is that your parameters are not getting updated, and thus your gradient is, because your gradient is near to zero. Key drivers to know the expressibility of things is a larger n, exponentially would give a larger space. A circuit depth, if you have more depth, more layers would be there, more parameters would be there, and higher expressibility would be there. Then gate set diversity is also there. If you mix rotation gates x in x, y, z, and you use entanglement, so you can increase your coverage. Now let's take an example. Now let's take a circuit A. I would only use rotation along z axis. Okay, and in circuit B, I use two rotation gates. One is along z axis and one is along x axis. Now, if I run this and plot their block spheres, so let's see how they would look like. So you can see the block sphere in the first circuit, circuit A, you are restricted to this equator only because it is rotation along z axis, which is nothing but this. So you are stuck here. But for circuit B, you can explore the whole Hilbert space or the whole block sphere. Thus, if let's say if your my answer is here, this circuit A won't be able to get here, and I won't get a good accuracy. But my circuit B would be able to get here. Thus, more expressible your circuit is, more generalizable your quantum circuit is, and thus it would be much more generalizable on your data, and you would have higher accuracy on testing. Now, the second thing is entangling capability of a quantum circuit. Basic definition is circuit's ability to generate multi-qubit entanglement from product or unentangled inputs. Basically, it is fundamental for quantum advantage in ML and optimization. If you have insufficient entanglement, your circuit would behave classically, that is linearly. And if you have excessive entanglement, your circuit would be very noise sensitive. Now, circuit features would basically include placement of two qubit gates, which is C0, CZ gate, or control rotation gates. Connectivity, linear versus full. Linear basically means qubit 1 is connected to qubit 2 is connected to qubit 3, and qubit 3 is connected to qubit 4 in a linear way. But full entanglement would be each and every qubit is connected to each other via entanglement gates. And as well as number of entangling layers. You can increase your entangling layers up to whatever you want. Now, how do you measure entangling capability? So basically, there are two ways. First is entanglement entropy. Let's say you have an n qubit circuit. Now, what you do is you cut the circuit into two groups. You take any random k which is less than n, and then you compute the surprise or the basically entanglement or entropy in one group, that is the k, via von Neumann entropy, and thus it would give you overall connectedness between the first half 0 to k and the second half k plus 1 to n. But it gets hard to calculate if your n increases very much, your qubit size increases, and thus you do not know where to cut. So there is one more thing, one more way you can do that is Mayer-Wallach score. Basically, it tells you how much each qubit is sharing information with the rest. Basically, it is a quick check of global entanglement strength, but it does not say which qubits are talking to which. Now, let's say if I only entangle qubit 1 and qubit 2, I am all the entanglement gates I have put in qubit 1 and qubit between qubit 1 and qubit 2, and qubit 3 and qubit 4 are not entangled. So my Mayer-Wallach score may be high, but it won't tell me which qubits are talking to which. Now the ansatz, that is your basically quantum circuit. Uh, there are two ways to design your ansatz. First is you can use an hardware efficient ansatz. Basically, you create circuits that match to device topology. That is the quantum computer that you are going to run on. It can be layers of native gates, repeated rotation gates, plus C0 pairs if your device has sorry, if your device has capabilities to execute C0, and it would be low depth because it is hardware efficient. It would be low depth, your depth would be less, and thus your it would have less noise. but it would have limited expressibility for complex problems. So second way to design is problem inspired. Basically, your Hamiltonian or your quantum circuit would reflect your problem. Basically, take your problem, you design your Hamiltonian, and according to your Hamiltonian, you would get your quantum circuit. And thus, because it is problem inspired, it would be able to capture domain specific features much more efficiently. But this would be very much deeper, and thus it would have much more noise, and it is device dependent. If your quantum computer does not have some gates, you would have to skip that. There is something called as expressibility versus trainability trade-off is also there. Basically, trainability is ease of optimizing your parameters, that is your theta, to avoid barren plateaus, that is the gradients becoming zero. But if you have a very high expressible circuit, you risk getting barren plateaus, that is the flat gradients. But if you have shallow or constrained ansatz, that is hardware efficient ansatz, it would be easier to train, but it would be very much less flexible. Now coming to gradient computation. Now, as you know, we have to find out the gradients, as is the case for any machine learning algorithms. But as compared to machine learning algorithms, where you can peek into any of the layers, like in neural networks, and see what the output is, you cannot do that in quantum circuits, because you, unlike classical neural networks, you cannot peek inside a quantum circuit without collapsing its state. So let's see. If you see here, I have to measure here. I cannot go and measure here, because if I measure here to find out what the state was here, I have collapsed my state and I cannot do correct measurements here. In classical neural networks, you could go behind a layer and do that, but in quantum circuits, you cannot do that, because after measurement, you do not know what the state was here unless you run the circuit again and measure here. So what do you use for gradient computation? Because you cannot peek inside the circuit, so you use something called as parameter shift. Basically, it is a gradient estimator requiring only two circuit evaluations per parameter. So any parameter gate you have, P is nothing but Pauli matrices. What you would do is, you would take your theta and add pi by 2 to it, and then you run your circuit, and then subtract pi by 2 from that parameter, and then again run your circuit and take the average difference of it. Thus you would give, it would give exact gradient in ideal cases, and you would not need any finite difference approximations like you use in classical neural networks. And thus it is easy to extend to multi-parameter ansatz and hybrid optimization loops. That is the current hybrid quantum enhanced machine learning algorithms. So a little bit more about parameter shift rule. Basically, a parameter theta, how it affects the output. You run the circuit twice, one with theta plus some delta, and once with theta minus some delta, and then compare the results. Basically, if you want finite differences, exact finite differences, you choose delta equal to pi by 2, which would give you an exact gradient without numerical error. And why it would work? Because quantum gates are rotations, and then thus shifting the rotation angle by plus or minus pi by 2 and averaging the corresponding exact would give you the exact derivative. Thus in practice, you would take your theta and have pi by 2 and get the expectation value, and then again with theta minus pi by 2 and get the expectation value, and then take the average difference of it. Now, how does QML workflow happens? Basically, you load your data, normalize your data, select your features, how many features you want, normalize it. Like let's say two iris flower measurements. Then you do quantum encoding. You can use angle encoding or your own quantum feature maps to uh, encode your features into qubit rotations. Then that variational circuit This circuit would be connected to your encoding, which would entangle and rotate qubits with trainable parameters so that you can optimize. Measurement would be there so that you can find the expectation value per qubit, and so that that corresponds to raw model outputs. And then you use optimization, classical optimizers like Adam, Ada Delta, to update the theta. Now this is classical ML versus quantum ML. Basically, classical time complexity versus quantum time complexity. Some cases are practical cases. So, for example, this quantum SVM. In actuality, we would require root m, where m is the number of samples. But in practice, in today, it is m to the power 4.67, which is very much worse as compared to classical SVM. Then there is k-means clustering also. K is the number of clusters, n is the number of samples, d is the dimension, and iterations. And if we have quantum RAM access, it would provide you quadratic speed up in n, that is the number of samples. Similarly goes for k nearest neighbor, you would have root n, and lower rank recommendation, you would have polylog mn. Now, how quantum enhanced machine learning works? Basically, the flow chart of it. Basically, you prepare the state preparation happens, your PQC runs, your quantum circuit runs, you get an output, you give it to your cost function, it calculates the cost, then cost function gives it to an optimizer, then you update your theta, then again state preparation has to happen because the quantum circuit has to run again, and because the parameters have changed, and then you again run your PQC, do measurements, out again you get the output, cost, update, and this cycle goes on until you converge. Now basically, why I had said that you take poly z expectation values. Basically, measuring in the z basis or taking allows us to directly determine the probabilities of a quantum state collapsing to either 0 or 1, because poly z expectation values, if it is positive 1, it would correspond to 0 state, and negative 1, it would correspond to state 1. Now if you see here, there is very easy mapping of it. Thus, by focusing on poly z, the process of extracting information from the quantum state is very much simplified, making it easier to integrate with classical machine learning algorithms. That is the current era of quantum enhanced machine learning. This also reduces the overall error in QML application, which is very much crucial given the current limitations in quantum hardware. Now, how QSVM works? QSVM basically involves a kernel function that computes the similarity. Basically, similarity between these points. These data points are much more similar, and these data points are much more different. Thus, your kernel, SVM kernel, would map it to a higher dimension, and thus you would be able to correctly separate them out. Similar case, we can use kernels like our feature maps in QSVM, which would measure similarity between the quantum states, basically their fidelity. This is nothing but fidelity of two quantum states if you encode these into quantum states. Now, how can you use quantum properties? Like quantum superposition, each data point can be represented by a quantum state that can be in a superposition of different basis state. Like we had seen amplitude encoding, you can compress 1000 features into 10 qubits. Or let's say if you try to use angle encoding. In this example, x is you have two features, and then you can encode it as alpha into 0 0, alpha 1 into 0 1, 1 0, and 1 1 states, where alpha I would be your coefficient representing the different feature values. Basically, this has been encoded into this state. You can also use quantum entanglement to help compute complex kernel functions that which would capture non-trivial relationship between the data points. If you see here, there is a non-trivial relationship. There is no one single line that can separate them out. Thus, with entanglement, you can see the similarities between them as well as separate them out. Now, there is something known as convolution neural network. especially quantum convolutional neural network. How it works is basically you pre-process the images and rescale them to 0 to 1. You have to normalize your images. And currently there are two ways to do quantum convolution. First is you use classical convolution methods and then give it to a quantum layer. Basically you convolve using classical, and then you flatten them and then process or extract features classically and then give it to your quantum layer. Other way is you use the quantum circuit itself to convolve on the that image. Let's say 3 by 3, so you use 9 qubits, and then you give convolve. How you convolve classically, you go here, take the go here, take 9 pixels, you convolve on this, you would get a feature, and then you would go slide again and again, and then you would get your features. Basically then the output is then again evaluated against class metrics that we are trying to optimize, like accuracy, precision, recall. So how can you use quantum properties in CNN? Quantum superposition. By leveraging superposition, the QCNN can perform feature extraction more efficiently, processing all locations simultaneously rather than sequentially. Like in classical, you go sequentially. You convolve here, then here, then here, then here, then here. So how you can do that in quantum? Let's say that this whole slide is an image. So what you do is you give this whole image to the quantum circuit, using where each and every pixel is encoded to a qubit. Thus, this parallelism can provide a computational advantage because everything is going at once, and thus reducing the number of operations required to process high dimensional data. You can also use entanglement. The QCN model dependencies between can model distant dependency between the distant regions of the input, which is particularly valuable in tasks like pattern recognition or anomaly detection. Now, let's say if this part and this part are related, so using quantum convolution, you can with entanglement you can know that these and these are related to each other. It is very much useful in MRI or CT scan, where you need to identify irregularities or abnormalities that may indicate tumors. Now, how you can do quantum NLP? Basically, a GPT, or your generative pre-trained transformer, uh, which is nothing but a type of large language model, utilizes probability to predict the next token one at a time. Now, if you do use quantum NLP using quantum GPT, if it which is possible in near future, you would be able to generate. Let's say this is the answer of your question. It would be able to generate this at in one go instead of generating it one by one. So thus you would thus the quantum circuits would can also compute attention scores in parallel as well. Like let's say how this is related to this, how this is related to this, can be done in parallel as well by leveraging quantum parallelism, basically uh, superposition. How quantum properties can be used? Quantum entanglement, which would allow the model to capture complex dependencies and relationship between tokens. Now my let's say we have a sentence, my name is Sachin, and he is giving a presentation. Now Sachin and he are connected to each other. So if the name changes or even the gender of it changes, the pronoun also changes. Thus, using quantum entanglement, you can map the relationship between two different tokens. You can also use quantum superposition. Like let's say each and every token, each and every word may have different meanings. So the each and every meaning would remain in a superposition, and when you measure it according to the context, you would get different grammatical tenses. Like let's say saw, one example is actually seeing, other example is that saw which is used to cut. So depending on the context, after measurement, uh, you would get the uh, correct meaning of the word. Now some applications of QML. basically you use for quantum data classification. Like you can use it in finance and healthcare, where data classification is crucial, and thus QML can enhance the speed and accuracy of categorizing the data, especially like in medical imaging. And you can also use for quantum chemistry and drug discovery, where it would be applied to simulate molecular structures more efficiently, very complex molecular structures, which would aid in discovery of new drugs. You can also use it in NLP, which is a little bit future prospect, where quantum computing could enhance NLP tasks like translation and sentiment analysis, as well as summarization. And advanced cryptography and cybersecurity, which is also a little bit future prospect, where quantum machine learning could be used to create more secure encryption methods and detect anomalies in network traffic much more faster. So, what are the limitations and open challenges in quantum machine learning? Basically, qubit count and coherence. Current NISQ devices have very few usable qubits with very less coherence times. That means their entanglement, the time that they remain entangled is very less. Thus, it is limiting your algorithm's depth and data size. Error correction overhead, as today's quantum computers are very much prone, so you have to achieve a very fault tolerance uh, quantum computers to encode uh, your data, basically in logical qubits as compared to physical qubits, with overhead which would grow exponentially in physical qubits. Then you have hardware engineering, like scaling beyond tens of qubits would demand complex cryogenics. Like if you see any image of a quantum computer, you see a very big uh, concoction. That is nothing but something to cool it. That is the cryogenics, and those control electronics, which would introduce latency and thermal noise as well. And practical speed ups, theoretically quantum advantage is there, but if you do that on real hardware, due to limited qubit counts and higher rate, it vanishes. But as your quantum computers evolve, you would be able to see theoretical quantum advantage in practical applications. Then barren plateaus, vanishing gradients, basically your gradients or become near to zero, thus you won't be able to update your parameters, and thus you would require much more evaluations to find a correct descending direction. Depth and connectivity, even shallow circuits with global cost functions can enter barren regions, thus making ANSAT design very much crucial. Then mitigation efforts, layer-wise training and structure ANSATs would can show promises, but no universal cure exists. And you also need optimizations, correct quantum optimizations. That is very research area right now. And noise induced plateaus, real devices are have noises which would then go into your gradients, and thus would require sophisticated error mitigation techniques. Then one other thing is data loading bottlenecks. You are in each and every iteration you are loading your data again and again. So until unless that is fixed, this quantum data bottleneck would be there. Like mapping data of n dimensional data currently into qubits is still on, and it relies heavily on quantum RAM, which is still largely theoretical. And you would require high dimensional inputs are also there. Unstructured structured data like images, you in classical you use 28 by 28 or 512 by 512, which is very high dimension. Thus it also drastically increase your circuit depth and gate count for amplitude or angle encoding. Then currently classical to quantum input or output operations are still there, like the hybrid QML. Basically classical processing happens, then it has to be encoded to quantum, then it goes to quantum processor, then it comes back, and then it has to be again converted to classical data, so that input output overhead is still there. And advanced loading schemes, where techniques like quantum GANs or Boltzmann machines would streamline your data but would introduce extra circuit complexity. Like I had told you, like these quantum GANs and Boltzmann machine would find out the complex relationship on your data, and you don't have to then like encoded, you would just give the classical and then it would be automatically encoded to quantum. But this is still a very future prospect. It is now currently not being done. So these are the resources you can use for QML. You can go to Quantum ML YouTube channel. It would tell you the mathematics of it. You can read research papers by Maria Schuld and Seth Lloyd. You can also go to this Springer journal, Quantum Machine Intelligence, which for current, uh, latest and current research. Then there is IBM Quantum Experience as well. You can also use Qiskit Machine Learning and Palindale libraries for your QML applications. This book, A Practical Guide to Quantum Machine Learning and Quantum Optimization, this book by Publishing, is basically taking you from zero to quantum machine learning. Basically, it would tell you what is quantum computer, what are qubits and everything up to quantum machine learning. So you can refer to this book as well. Uh, for Indian audiences, this is approximately 800 rupees for the ebook. You can download it from Publishing channel as well. So this with this we come to the end of our PPT. Now let's move on to our Qniverse. So this is our Qniverse. Let me log in and show you the quantum machine learning algorithms that are available for you to use in our Qniverse. So, sorry for that. So this is our Qniverse. Basically, yes. So let me go to this algorithm section. I'll quickly show you some of the algorithms because I think we are running out of time. Let me load this QSVM algorithm. You basically choose your file, you choose your labels, what you want to predict, the test size, your kernel, like these are the various available kernels here, and the max number of iterations. So let me load a very basic simple example. And you would reach here, and currently we have restricted it to CPU, but for GPU and other things in future you would be able to run your quantum machine learning applications on GPU and QPU as well. So then you submit it, you get your job ID. Let's take one more small example. Let me take a QPCA example to show you how you can do that. You can choose your file. Let me take this file, wine.csv file. Now it has been loaded. I can see these are all the features that are available, and I'll select target as what is the target. Then I'll load it. Then I'll run it. I think our QSVM has trained. So let's see where till QPCA trains. Now, if you see here on the right hand side, you would be able to see what kernel you have used, what was the loss for that iteration, and what is the best loss out of all the iteration, what is the accuracy of that iteration, precision, recall, F1 score, and everything. Let me come here, sorry. And then you would see what is the lowest loss that was observed, which is nothing but it was in epoch 3 here. These are the predictions on your test data and what is the optimal parameters that has been calculated for weights and biases. This basically corresponds to weight of each of the numerical column and the bias. Then the performance on the test matrix and your classification report. Because the number of samples were low, so you have a very bad training. But if you use a good kernel, we also use a linear kernel, which is also very bad for classification of this. But if you use some other kernel, you would be able to get much higher accuracy. And on the left hand side, you would see how in each and every iteration, your loss, your accuracy, F1, loss, precision, and recall were changing. And if you click here, you can also see the confusion matrix of it, because this model was not good. So you can see that as compared to what it has to actually had to predict Setosa, it did not predict, but it gave a false positive and false negative, true negative results. So now let's see the other algorithm, our QPCA algorithm. For that, I think my internet is a little bit slow. Let me refresh this. Yeah. So basically, whatever the target column was had to be removed. So now, what happens in our PCA using quantum phase estimation? First, we use 4 ancilla qubits to find out your uh, average relative error between your classically found out covariance matrix as compared to quantum found out covariance matrix using quantum PCA. Basically, what we have to do is basically uh, reduce this average relative error. Currently, we have set it to 50%. So now if you see it is more than that, so large discrepancy is there, so we need to increase our number of ancilla qubits. Then you increase it, but now if you see it has increased more, so now you have to increase it again, and now it is still more. So it would still go on up to 4 attempts. If it does not have, it would try to use the ancilla with which you got the least error. And now this is the dimensionality reduction error. This is the density matrix of your features, and this is the unitary matrix. It is very long because we have a lot number of features. These are the measurement distributions found out from QP simulation, and these are the estimated eigenvalues that have been derived for each component. Now if you see here, each principal component comprises of, these are the top five feature loadings. That means this flavonoid corresponds to 0.4% change in this principal component 1, and this principal component corresponds to 45% of your total variance. Similarly for component 2, it corresponds to 36. And we have extracted approximately 4 components, and thus if you see detailed eigenvalue analysis is also there. So let's say if you want to have 80% variation rotation, you can use first. If you want 90%, you can use two components, both the component 1 and component 2. And these are all the other metrics that it would tell you how your principal component analysis has worked. So with this, I end my presentation. This is the end of it. I hand over to our panel member.
Hi, Sachin.
Hi, sir.
Yeah, the last few examples which you showed on Qniverse, I hope there will be a detailed explanation of any one of the algorithm in the next session.
Yes, in the next section, we have two algorithms that we'll take, quantum SVM and quantum K-means, and then we'll do a detailed session on it.
Yeah, because you just covered the introduction and you showed the demo
Yes.
of Qniverse on the Qniverse. So the participants might think, may not know the exact context. Yeah, that's good
Yes.
that you will be covering in our next session. Uh, yeah, there are few questions. I'll just read out. Vinayaka VM was asking, can NLP be done?
Yes.
However, you answered in the future slides. That's okay. The next question is by Ranjan Balaji. Which rotation is an efficient one? Which combination of rotation is preferred?
So there is no one preferred rotation. So you can use a combination of it. Just ensure that you do not use one single rotation for everything. Like you do not use RZ only for everything. You have to use a combination of it. This combination is usually dependent on your data set or your problem. So there is no one efficient way. There are multiple ways, but there is no one efficient way.
Okay. Uh, Naseem Kuchi, he is asking, in quantum algorithms, is the speed up and efficiency is important? How can we measure the speed in quantum machine learning?
Basically, it is measured mathematically. Those all theoretically they are measured, but practically in current era it is not there. But as the quantum like hardware improves, you would be able to see the theoretical gains in the practical application as well.
Okay.
But currently you cannot measure it. That's because of uh, current era.
Okay, which I mean, I have one question which links to this. How many fault tolerant qubits you expect for any use
Human
case to
aspect.
be demonstrated?
Fault tolerant qubits basically depends on your data, but if you see the real world data, it comprises of more than like 1,000 features. If you see, some toy data sets are there which comprise of 10 to 20 features, but if you go to a real world data set, they comprise of thousands of features. So depending on what encoding scheme you are using, the number of logical qubits would be there. Like let's say if you're using angle encoding, you would need 1,000, like 1,000 features are that you need 1,000 logical qubits, which also are comprised of physical qubits. So the qubit count would be very much higher.
Okay. Ahsan ul Haq, which type of data needs which type of encoding? I think you answered this question.
Yes.
Right. Sumanta Chakraborty, she is asking, classical ML requires a huge volume of data. To map this to QML, we need then a huge number of qubits, but we are available with a very low number of qubits. So how do researchers perform QML experiments in these circumstances?
Basically, what QML experimentation has been done is on hybrid approach. As I had said, basically what you're doing is using principal component analysis like classical PCA to reduce the number of features, and then on those features you do quantum machine learning. Like let's say from 1,000 features you shrink it down to 10 features, and then with those 10 features you can use angle encoding or any encoding principle you want, and then do QML on it. Basically,
Okay.
yes, because of like very low number of qubit count that is currently available, you can only use toy data sets. But as the quantum computers enhance, so you can go with real world data sets as well.
Right. Next question is by Ranjan Bala Jain. Optimization is done on classical or quantum computers?
Currently it is done on classical computers, so whatever expectation values you get, you would then give it to classical computers, and then optimization would happen. Currently quantum optimization algorithms are there, but they still rely on classical computers to optimize it. But as our research happens and uh, correct or efficient quantum optimization algorithms are there, then they would be done directly on quantum computers instead of classical computers.
Okay. Um, Bhaskar asks, how fix dimensionality curves in fraud detection and anomaly detection using QML? Like same
You
name in the given list and same features until we come to last parameter or only one parameter differentiation.
Okay, you can fix the dimensionality curves by using amplitude encoding. Like you do not need to then shrink your data, but the thing is, with that many number of features, you need that many number of qubits as well, so that you can get in higher dimension as well. As because each qubit remains in a two-dimensional Hilbert space, so n qubit remain in 2 to the power n dimension. So curse of dimensionality would not be there if you use sufficient number of qubits, and thus like going on that, if like let's say you can also use quantum principal component analysis as well to find out the correct what can I say principal components that you can use, and thus you would also fix the dimensionality curse.
Okay. Next question is by Naseem. Can quantum machine learning can count the percentage of microplastic present in the blood, where 90% accuracy has been found present of microplastic by someone regarding this in any other project work? Or is there any other process? How can we overcome these challenges? I think
uh,
he's asking for a specific use case of UML.
Yes, this percentage, I don't know, but you can do with probability. Like instead of percentage, you can do probability that 90% probability is there that there is going to be microplastic in there. Current scenario is that, but as algorithms would advance, then we can come to this percentage as well with probability as well as the percentage as well.
Okay. Uh, Ramesh, may I request to share or upload PPT or presentation on GitHub page? Yes, it will be done. Rajesh asks, what are the various ways for encoding images into quantum?
Basically, there are, I think, two ways. One is feature representation quantum encoding FRQI, and there is new quantum encoding state. I'm sorry, I'm unable to recall it, but there are two ways to do that, which are very much efficient for today's NISQ eras. I'm
Uh,
unable to recall it right now, but I would surely give it to you if you
yeah,
personally have.
probably next session, if you can collect the data, you can tell them.
Sure, sure.
Uh, he is also asking, can we encode videos also?
Videos basically, if you translate it, it is nothing but number of images per second. So how you encode images, you would encode them step by step.
Okay. Pradeep asks, how to store model just like .pkl file?
You basically store the parameters, the this structure of it, but basically you cannot actually store it in pkl file as is the case for classical models. So you have I don't know, currently I don't know how to do that, but if you have a hybrid model, you would be able to store it with the parameters and the circuit structure written to it, not like the actual quantum circuit, but the structure of it like written there.
Next question is by Rihan Khan. Can you suggest some research gap at a generic point with respect to QML?
Whatever I those pain points are there, like the barren plateaus is there. One of the basic or the most general thing is barren plateaus, how you can mitigate barren plateaus in your qml applications. Then qubit count scalability is also there, how you can efficiently map a very high number of data or high feature of data into smaller qubits, so that you can efficiently use quantum computing, quantum machine learning.
Okay. Yeah, with this, we come to the end of the session. Thank you, Sachin. Thanks very much for the deep dive into introduction to quantum machine learning. And hopefully, we will come learn the specific algorithm of quantum machine learning in our next session. Thank you all the participants for joining on this occasion. I mean, even though it is a Dasara festival times, you all have been with us and you have joined at this. Thank you very much for all the participants. And I just would like to reiterate some of um, the notifications. One second. Yeah. So for the quiz questions, I apologize that for week 9, 10, and or 10, 11, 12, sorry, 9, 10, 11, we will share it very soon. And regarding the participation certificates, yes, of course, we will share the form for you all to fill up your exact name, which it should appear on the participation certificate. Then on the Qniverse developer certification, we are working out on the various things like to get the registration, the fees, the exam format, and other information like the dates, when to conduct. Uh, Please follow us our YouTube, WhatsApp public channel, and through email we will notify you. So with this, we come to the end of the session. Thank you all for joining and happy festival times. Happy Dasra. Thank you all.